Imagine we have a block resting on the ground, and I am standing on the block. Someone comes along with a meter stick and says, this block is 1.0 plus or minus 0.2 meters high, and your height is 1.3 plus or minus 0.1 meter high. This plus or minus is called the absolute uncertainty. It has units. The meters apply to the measurement and the uncertainty. And we typically round absolute uncertainty just to 1 sig fig. So if I ask, how high is my head off of the ground, that's easy. Let's call the first measurement A and the second B. This new value we'll call y. Well, to find y, you just add. But that's easy enough, and we do 1.3 plus 1 to get 2.3. But how uncertain is this value? I mean, after all, 2.3 is coming from measurements that have uncertainty. What do we do with those uncertainties to find the uncertainty in y? We will use a triangle to represent uncertainty, the absolute uncertainty. So the delta here means two things. It could mean change in, or it could mean the uncertainty in. So the absolute uncertainty, delta, the absolute uncertainty in y, we find it by adding the absolute uncertainties in our measurements. In other words, we have to add the 0.1 and the 0.2 to get a total uncertainty of plus or minus 0.3. That means y is equal to 2.3 plus or minus 0.3 meters. This might make some sense intuitively. After all, this box right here could be a little bit higher, 0.2 meters higher. And if it were, my feet would be up here. And then my head could be 0.1 meters higher. So on the whole, the entire measurement could be 0.3 higher. That's what this says, plus 0.3. And by the same reasoning, we could say that the block is actually a little bit lower, putting my feet down here, and so is my head a little bit lower. Combining those effects means that the total, or the sum, could be 0.3 lower, adding again just 0.1 and 0.2. Imagine I have two blocks. I measure the height of blue, then I stack the black one on top, and then I measure the total height. The question is, how tall is just the black box? Well, that's easy. We take the first measurement, A, we subtract the second measurement, B, and the y, the new value, is, in this case, 3 minus 2, that's 1. But what's the uncertainty in y? The rule says the uncertainty in y is found by adding the 0.1 uncertainty with the 0.2 uncertainty. This gives a total uncertainty of 0.3. To understand why this makes sense, we do something similar to the prior example. How big could this block y actually be? Well, maybe the total is 0.1 higher, and maybe blue is 0.2 lower. That means that the black would be 0.3 bigger than we originally had measured. Similarly, perhaps the blue alone is actually 2.2, perhaps the total is actually 2.9, and how much height have we shaved off of y? We've taken away 0.3. So yes, the uncertainty in y is plus 0.3 or potentially minus 0.3. And so the rule of adding the absolute uncertainties from this guy and this guy, it's the same rule as before. Let's summarize. If we have two measurements A and B, and we add them to find y, the uncertainty rule says add the absolute uncertainties. But if we have two measurements A and B, and we subtract them to calculate a new value, it's the same rule, add the absolute uncertainties. What if we multiply or divide? Well, if we multiply A times B, instead of simply adding the absolute uncertainties, we have to add something called the fractional uncertainties, or the percentage uncertainties. So if I told you that I measured the time it takes for a ball to fall, and the uncertainty is plus or minus 0.1 second, is that a big uncertainty or a small uncertainty? Well, it depends. If the ball was only in the air for 0.2 seconds, then this is quite big by comparison. But if the ball was in the air for 1,000.2 seconds, this is quite small by comparison. Absolute uncertainty doesn't always tell us the whole story. Sometimes we have to take the absolute uncertainty and divide by the measurement. And then we can see, is the uncertainty large or small relatively? We call this the relative uncertainty, or the fractional uncertainty, or the percentage uncertainty. So here's how we write it. We say the percentage uncertainty in Y, which is the absolute over the measurement, is equal to the percentage uncertainty in A plus the percentage uncertainty in B. Unfortunately, there's no symbol for the fractional or percentage uncertainty, but we could, if we want, say the percent in A is equal to the percent in B plus the percent in C. What if we take this and we add some division into the mix? Well, in that case, we simply continue the exact same rule. For multiplying and dividing, we add the fractional or percentage uncertainties. For adding and subtracting, we add the absolute uncertainties. Here's a sample problem. We have this formula, and we're given values of A, B, and C. Okay, this is pretty straightforward, and first we have to find the value of Y. Well, we just plug in. The problem should have stated to include units, so let me do that as part of my work. A, B, those are in the numerator. A is 2.0 meters, B is 1.5 seconds, C is down below, and it's 2.5 meters. So what happens with units? The meters cancel, and Y will have units of seconds. So if we perform this calculation, you can, no shame in getting out a calculator. We have 2 times 1.5 over 2.5, and we get 1.2. Now what we have to do is, for part B, find the percentage uncertainty in Y. So I'm going to do percent in Y is equal to the percent uncertainty in A plus the percent in B plus the percent in C. The percent in Y is my final unknown. How do I find the percent uncertainty in A? Well, I do the ratio. A's uncertainty is 0.5 meters, and its value is 2.0. Notice how the units will cancel. B has an uncertainty of 0.1. The value is 1.5. C has an uncertainty of 0.3. The value is 2.5. The measurement is 2.5. So let's do this in our calculator. We've got 0.5 over 2 plus 0.1 over 1.5, whoops, plus 0.3 over 2.5. And when we put this all together, wow, 0.44, and if we convert to a percentage, 44%. That is a very high percentage. That is not a great experiment. Okay, last question says, find the absolute uncertainty in, this should say Y. So here's what we do. The percent uncertainty in Y, or in any value, is always the absolute uncertainty over the value itself. We know the percentage, we know Y, 1.2 seconds, so we can go calculate delta Y, the absolute uncertainty. Okay, so let me put this back into a decimal. 0.4, what was it, 36, dot, 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 is equal to the absolute uncertainty over the measurement of y itself, which comes to 1.2 seconds. We cross multiply, and we get a final answer of 0.5, plus or minus 0.5. The absolute uncertainty has units, and we give it 1 sig fig. We are done.